I think I think we are live. So hey everyone, let me know if you guys can hear me properly. Uh, if I'm audible. Let me know if you guys can hear me. Yep, I can hear myself. Okay, so I think I'm audible. So yes, how did the contest go? I already see Piyush has mentioned that the question is not correctly. Not sure what that means. Was last question rerouting DP? Last question minimum sum, no, it is DSU based question. It is a DSU based question. Yes. Okay, Victor, thank you. Cool. How were the questions overall? Like, did you like the questions? Were they difficult, easy? How would you rate the difficulty? Question was not correctly written. Okay, got it. Which one? Some typos were there. Okay. Okay. Anyways, let's look into the problem statement. Uh, okay, I see this one. Got it. So the first question is Victor is saying the questions were difficult. All right. So we'll see how do we solve them. I'll try to solve them. Okay. So the first question is dominant pairs, right? So the question is you are given an array of integers of size n, where n being even. You have to calculate the number of dominant pairs ij, where a pair is called dominant if 0 less than equal to I n by 2, that is a less than equal to sign should have been there, and n by 2. Okay, so this is something like this, that 1 second, the expression would have been something like this, that hey, 0 less than equal to I less than equal to n by 2 less than equal to j less than n. I think that was the last sorry, yep. So j, yes, j, and it is greater than 5 into arr. Arr I is greater than 5 into arr j. Okay, got it. So also one more constraint here is that arr I is greater than 5 into arr j. So this was the question, right? 5 into arr j greater than equal to, or greater than equal to. Okay, so this was the question, that 0 is less than equal to I less than equal to n by 2 less than equal to j, means I should be in the range. So what is the range in which I should be? I should be in the range 0 to n by 2 minus 1, and sorry, 0 to n by 2, and j should be maybe n by 2 plus 1 to or I think it should be less than n by 2, and j should be from n by 2 to n minus 1. We'll figure it out, but yeah, so this should be the range, right? Cool. Okay, so that is the question. Now this relation is fulfilled. For example, arr 10 3 3 1, right? If you see 10 and I equals to 0, j equals to 3, it is satisfying the condition, right? It is satisfying the condition. In fact, n is 4 by 2, so it is in fact less than equal to 0 1. Okay, 0 1, yeah, it is less than n by 2. Cool. So 10 3, this is where I will loop into 10 and 3, and this 3 and 1 is the loop for j, right? And I equals to 0, j equals to 3 is forming a dominating pair, and similarly I equals to 0, j equals to 2 is also forming a dominating pair, right? I think 5 into 3, no, 15, 15 is not 10 is not greater than 15, so it will not form a dominating pair. So there is only one dominating pair, that is 10 and this one, right? So again, for example, 10 2 2 1, in this case 10 2 are forming the loop for I, like I will loop from 10 and this across this 10 and 2, and there will be 2 and 1, so 2 and 1 will be looped by j. And so the condition that we have to satisfy is j arr is greater than equal to 5 into arr j. So is arr I, that is 10, greater than equal to 5 into 2. Yes, 5 into 2 is 10, greater than equal to, so it is. So this 0 and 2 is satisfying the condition. Similarly 0 and 3 will also satisfy the condition. With 1, nothing, none of them actually satisfy the condition, right? So the answer will be 2 for this. The answer will be 2 for this. Okay, so that should be it, and we have to do it like n is 10 to the power 4 and ARRI is 10 to the power 4, so that should be the complexity. Okay, so this should be the, this is the question. Yes, there was some typo in this part, right? 2 less than equal to got mixed up, and there should have been a comma here as well. So it's a typo in this part, but yeah, like that is the question. I less than n by 2 less than equal to j, and ARRI is greater than equal to 5 into ARRJ. Yeah, so yeah, like similar thing. So what we can do is, how do we solve this? So we want to find for each element, if it is greater than 5 into like how many elements are there for which it will be greater than 5 into ARRJ, right? So basically let's say 10 to 21, let's take this example, right? 10 to 21. Okay, we have, let's clear this up quickly. Ten to 1. Now what do we want? We want on the second half, like kind of we are treating two arrays, right? We have two arrays. The first array is 10 to, the second array is 2 to 1, right? Because it is already said the first half will be traveled by I, the second half will be traveled by j, right? So it is kind of, we are breaking it down into two arrays. Now it is saying that for each element you have to find how many elements in j are there such that ARRI, the current element, is greater than equal to 5 times ARRJ, right? So that is what is asked here. So what we can do is, we can sort both of them. We can sort both of them. 2. Okay. Okay, 2, and it should be. Let's sort both of them. 2, 10. Let's see how we can do this. So here it will be sorted again. 1, 2. Now for 2, we have to find the first index, right? We have to find the first index. What is the condition? See, initially it is sorted, right? So it is increasing this side, this will be increasing. So what do we want? We want the first index. This let's say this is run by j, so we want the first j such that ARR of j, right? ARR of j is less ARR of j, it is greater than 5 into ARRJ, it is greater than ARR of I, right? So see, ARR of j is increasing, ARR of j is increasing, right? So initially it will be small, so 5 into ARRJ will be small. As ARRJ grows, 5 into ARRJ will also grow. At some point it will be greater than ARR of I. So that is the point that we want, the first j that will satisfy this condition. Now n by 2 to j minus 1, this is the range that will actually satisfy our condition, that will be giving our answer, right? So that should be the answer, like these many elements for the current element. So for this, the first index that is not satisfying this, how do we find this, right? How do we find the first index that is not satisfying this? We can do a binary search, right? So we can do a binary search for ARRI on ARRJ, right? For ARRI, what we will do is, first only let's call them two arrays, right? Let's call them two arrays. So we will have two arrays, A and B. The A is the first half, 0 to n by 2 minus 1, and B is the second half, n by 2 to n minus 1. Now we'll sort both of them. Now what we'll do is, we'll do a binary search. We'll do a binary search on the second array, right, and find the index for every element of the first array, right? We can do that. And what is the, and also first of all we'll convert B. See, what do we compare? We compare with 5 into ARRJ. So we can just do B into 5. We convert all the elements of B into 5 into B, because what it matters to us is 5 into B. So we can just convert them into 5 into B, and then we can do a binary search, and we can quickly find the first index in the second half, such that B of index, now because B of index is already 5 into B of I, right? So B of index is basically greater than A of I, sorry, is greater than A of I. So that means we have to find that. So what we can do is lower bound. We can use a lower bound on this. Right, we can do a lower bound on this. Yes, first half sorting is not necessary. That's true. First half sorting is not necessary. We can do for the second half. In fact, this can also be solved. Like, if you want to make this better, right? Again, we'll write the code for binary search only. But if you want to make the complexity will be n log n by 2 log n by 2, that is n log n. But in fact, if you want to make it better, you can do a 2-pointer approach, right? You can do a 2-pointer approach. Note that if you sort both of the halves, right, your pointer in the second part will only move towards the right. Your pointer will only move towards the right. So that's why we can do a n log n approach, or it will only move towards left. How you sort? So you have to find the order in which you will sort, so that the second pointer only moves in one direction as you move the pointer in the first on the first list, right? So think about it. How do you solve it using a 2-pointer approach? And that will reduce the complexity to order of n, but will only will go ahead with binary search, because this is a simpler way to this will be simpler to write for us as of now, right? So let's write the code for this. Code dikhao please. Yes, let's write the code for this. So what we'll do is, let's actually first only break down into two parts, right? We can choose to break down, or we can not choose to break down. But again, like, it's better if we want to make the code like more understandable. Let's just break it down into two parts. So I equals to 0, I less than n by 2, I plus plus, a dot pushback, arri, for int j equals to n by 2, j less than n, j plus plus, b dot pushback, arr j. Right, now we'll sort the b. So sort b dot begin, b dot end, and also we'll convert this into 5 into b, right? So for int I equals to 0, I less than b dot size, that is n by 2 anyways, but let's do b dot size, I plus plus, b of I into equals to 5, b of I into equals to 5, right? Now what we'll do is, for int I equals to 0, dominant pairs, also answer we have to maintain, so number of dominant pairs. So int answer equals to 0, for int I equals to 0, I less than a dot size, that is n by 2 again, I plus plus. Now our current element is a of I. In the b, what do we want? We want the first index in b such that b of I is greater than the a of I value, basically, such that b of j, or let's call it b of j, is greater than a of I, right? First index j in b such that b of j is greater than a of I. That is what we want. So we'll do a upper bound, so a lower bound, int int index equals to lower bound b dot begin, b dot end. Now what does lower bound give? Lower bound gives the first index greater than equal to the current element, right? So we will not search for a of I, because we equality also we don't want, we want strictly greater than. So we'll search for lower bound of a of I plus 1, right? We'll search for lower bound of a of I plus 1, right? Because we want strictly greater than. So idx that and minus b dot begin, this will be the idx, right? So answer plus equals to idx, these many elements are there, right? These many elements are there. Answer plus equals to idx, these will form a dominant pair with so these many idx. See, let's say idx is 2, right? Let's say idx is 2, that is 0 and 1 will form a dominant pair with the a of I, current a of I, index 0 and 1 of b, right? So that means two elements, that is idx number of elements, are forming a dominant pair with a of I. So answer plus equals to a of idx will do that, answer plus equals to idx and return answer. So that should be the logic. Can you explain again the 2-pointer approach? Sure. I'll really like if you try it on yourself, but I'll give some hints, right? I'll just give some hints about this. So just think about it. Let's say this is your A, this is your B, right? We'll not assume like both of them are sorted, but what is the order in which they will be sorted, that is something that will not assume yet. But we'll only fix the ordering of A. Let's say A is ordered in increasing order, right? It is sorted in increasing order. That means as we move to the right in A, that will move, right? We'll move from 0, 1 to in A, we'll just do a loop. So we are moving to the right of A, similar to the loop that we have done here. Here we are doing binary search, right? Here we are doing a binary search on B and we are looping on A. So this loop will continue, but instead of binary search, we want to do a 2-pointer approach, right? So it is going in increasing order. What should be the order of B so that the pointer only moves, the right pointer only moves towards one direction, right? So this, in this way, A is increasing, right? A is increasing. Let's say B is also in increasing order. Does this work then? B is also in increasing order. So let's say for A of I in B, we get an index of J. That is, what does this mean? Index of J means B of J, or 5 into B of J basically. 5 into B of J is greater than A of I. The first index, right? For A of I, we get J. Now, as we move to the right, that is A of I plus 1, which direction will our pointer move? So, our pointer in the B array should also move which direction? A of I is increasing. So, we know that B of J is the first index that will satisfy 5 into B of J is greater than A of I. Now, our A of I value increased, right? So, there is a possibility that this J, this B of J becomes 5 into B of J becomes less than equal to A of I plus 1. There is a possibility definitely. But we are sure about this, that all the elements less than B of J, all the elements less than B of J will also satisfy this property. So our pointer in this as well will move to the right, because A of I value increased, right? A of I value increased, like A value increased here from A of I to A of I plus 1. This is increasing. So we want a better value of B as well, right? So that 5 of B of J becomes greater than A of I plus 1, or 5 into B of K greater than A of I plus 1. So definitely B of K should be greater than A of I, greater than equal to A of I. That's for sure. That's for sure, right? So K should also move, B of I, B of J. So K should be greater than, as it is sorted in increasing order, so K should be greater than equal to J. So if you see the right, this pointer also moves towards the right. So when the second pointer is also always moving, like as you move the first pointer to the right, the second pointer is also moving in one direction. This is 2-pointer, right? Both of them are moving in one direction. So once an element is covered, it is never visited again. So total complexity will become order of n. Right? Total complexity will become order of n. So try to write the code for this, but yeah, okay, there's a compilation error here. Let's see what is the compilation error that we are getting. Okay, dominant pairs. Oh, return answer, and there is a return statement here. Sorry, my bad. So let's try to run this. I think the 2-pointer approach is also clear. So try that yourself once, and I hope this works. It might. Let's see. Yeah. So this is working, right? And definitely try. The complexity for this will be, this is running for length n by 2. So n by 2 into, for every time you are doing a log n by 2 binary search. So n by 2 into log n by 2, that is n log n approximately. So with 2-pointer, it becomes reduces to order of n, right? So try the 2-pointer on your end, and this is the binary search approach. So pretty simple. I hope that this is clear with everyone. Okay. So let's go to the second question, and we'll use a new board for this. So let's create a new board as well here. Right. Okay, let's go to the second question. Yep. So good subtree. The problem is you are given a root of a binary tree and each node of the binary tree is assigned a value, and you are also given an integer k, and you have to return the count of good subtrees of this binary tree. Good subtree is a subtree such that the number of distinct values in the subtree is less than or equal to k. Right? So what it is told, you are given a binary tree, right? You are given a binary tree and each node has some value associated with it. Now what is a good subtree? A good subtree, you are given an integer k. A good subtree of the tree is the subtrees that under which the number of distinct values that come under that subtree is k, is less than or equal to k. The number of distinct values within the subtree should be less than equal to k, right? So that is a good subtree. You have to count the total number of good subtrees. Subtree of a node consists of that node and all the nodes in the subtrees of left and the right child of that node. So subtree, I think it is clear with everyone. So for example, subtree of 3 will only contain 3. Subtree of 2 will contain 2 and 3. This subtree of 2, this 2 will contain 2, 5, 4. Subtree of 5 will just contain 5. 4 will just contain 4. Subtree of 1 is the entire tree. So basically subtree means what? All the nodes that are coming under this node in the tree. Directly coming under this node. Not directly coming under, but they're under this node in the tree. Right? So that is a subtree. And you have to tell how many subtrees are there such that the number of distinct values in that subtree is less than or equal to k. Okay. So that is the question. So for example, here the output is 4, k is 2. So if you see for this 3, the number of distinct values in the subtree of 3 is 1. So this is satisfying. 5 and 4 are also satisfying. Number of distinct values is 1. So 3 is already done. For this 2, the number of distinct values under this subtree will be 2 and 3. So 2 values less than equal to 2. So it is also satisfying. For this 2, number of distinct values in the subtree is 2, 5, 4. 3 values. So it is not satisfying, less than equal to k. 1, under this 1, 2, 3, 4, 5. 5 distinct values, so again not satisfying. So only 4 of them are satisfying. So the answer is 4. Okay. So this is the question. How do you solve this? Anyone has any ideas on this? Anyone has any ideas? Anyone has any ideas on this? It's a very good question, and give some ideas around how can you approach, or what is the first thing that you should see in this question. DFS and set, okay, that's fine. Let them laugh. So basically I don't want to solve it in another language because again, like, it will take time. The idea of this session is to give you the idea. It's not about how do we write the code, it's about how do we solve the problem. I tell you how to solve the problem. If you are not familiar with C++, it is expected that you will try the problem on your end, right? Try to write the code in Java. Again, it's just simple for loop and these things, right? And if you don't know how to take a lower bound in Python or how to do binary search, you can definitely Google them up, right? How do we do a binary search in Python? Okay, DFS and set. Everyone is proposing a set solution. Okay, there are a lot of ideas, good ideas in fact. Okay, so many of you are telling DFS and set, which is definitely one way, and we can do that, right? DFS and set. The first thing that you should see, like, whenever, how do you get this idea that DFS and set? Because in worst case, the set can contain what? If all the values in the subtree are distinct, the set can contain n distinct values. But the idea here is that node.data is less than equal to 25. So the set size will never be more than 25. The size of the set will never be more than 25. So what you can do is you can maintain a set. So you can maintain a set for the subtree, and then you can merge two sets, right? You can easily merge two sets because you will just the set size will be 25. So you will just run a loop of 25. You will get the left subtree set, right subtree set. you are doing a DFS, right? In the current node, you will get the left subtree set of distinct values, right subtree set of distinct values. You will merge the two sets just by running a loop. And in the set size, you will get the number of distinct values in the subtree, and you will just see if it is less than equal to k or not. So this is the main observation here. Set is definitely one way. Can you think of any other way other than set to maintain this value, right? To maintain the value about number of distinct elements on the left subtree, number of distinct elements on the right subtree. Note that it is not only the fact that number of distinct elements, but what are the elements, that is also important. Because when we combine the two sets, we should be sure that we are not over counting or under counting. So what are the exact distinct elements, that is also important. So is there any other way other than set? And in fact, let's say I'm not comfortable with using any data structure at all. Is there any way to do it without using any data structure? Just think about it. 25, constraint is 25. You just want what are the elements that are present, and the elements range will be from 0 to 25 or 1 to 25. Array of size 25. That's one way, but I don't want to use any data structure. Any other way to know which elements are there, and when the size of the elements, when the number of elements will be 25, like the range will be 25, 1 to 25, without using any data structure, array, set, anything. You have to maintain which elements are present. Is there any data structure? Not data structure. Is there anything that helps us support that? Then I need n squared time. Okay, I'll tell you an idea, right? Actually, it's very simple, and we have discussed similar problem. Correct me if I'm wrong, I might be wrong as well. But my proposal is, why don't we use a bit mask? Why don't we use a bit mask, right? That is, we will have a mask of, the mask is what? It will be a simple integer, right? There will be 25 bits. 0, 0, like this, right? It will be like this. Let's say 2, 3 and 5, these are the values that are present, right, in the set. What will be the corresponding mask? 5th bit is set, 0th bit is not set, 0 is not there, 1 is not set, 2 is set, 3 is set, 4 is not set, 5 is set. So this is the corresponding integer value for this, whatever is the integer value that we can have, right? Or let's take a smaller value. Let's say in the subtree we have 1, 2 and 3. We have 1, 2, 3. So it will be 1, 1, 1, 0. That is what? 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3. 8, 12, 8 plus 4, 12. 14. We are getting 14, right? So this subtree, if the subtree has 1, 2, 3, this will return 14. What is bit mask? Bit mask means you are maintaining so just think about it. What does the integer represent? 0 represents 0 in binary. 1 is 0, 1. 2 is 1, 0. 3 is 1, 1. 4 is 1, 0, 0. 5 is 1, 0, 1. Like this, right? So if we assume each of these positions, each of these indices as the corresponding element, that means if 1 is present, the 0th bit will be set. If 0 is present, the 0th bit will be set. If 1 is present, the first bit will be set. If 2 is present, the second bit will be set. Like that, right? So what does this represent? This represents a set of only containing 0. This represents a set of only containing 1. This represents a set of containing 0 and 1. This represents a set containing only 2. This represents a set containing 0 and 2. Like that, right? So basically this is called bit mask. When you reduce an integer to its binary representation, the mask that you generate, this is called a mask. 0, 1, 0, 1, like this, right? That can represent a set of elements, right? That can represent a set of elements. How did you come up with this idea? It's a very simple strategy, right? Whenever you see, Again, I have repeated this, I've told this multiple times. Whenever you see the constraint are within 30, right, or in fact within 60, you can do a bit masking. Why? You can represent, and if you want to represent all of the elements independently, if you want to know which are the elements that are present, like each, if you have a question where you have to take a boolean array of size 30, right, you have to take a boolean array of size 30 or a boolean array of size 60, where it will represent whether an element is present or not. You can basically represent this as a bit mask as well. You can represent this as a bit mask as well. There is a lot of background sound because of Diwali. I hope you understand. I'm sorry about that. I cannot do anything about that. But yeah, so that is when we should use a bit mask, right? So what we'll do, the logic now reduces to something like this. Let's clear the content. How do we combine two nodes? Let's say in this node, the subtree of this node has 1, 2, 3. The subtree of this node has 1, 2, 3. How do you come up with the idea of bit mask? I already said, right? And the second node has 2 and 4, let's say. Now you are combining them. So what does this bit mask represent? This bit mask will represent 3, 2, 1, 0. This is the mask it will represent. This is the corresponding integer. It will represent 4, 3, 2, 1, 0. This it will represent. So what will this node represent? And obviously this node also has some value. Let's say this node has a value of let's say 2, right? So what will this node represent? This node's current value in bitmask format is 100, right? So this node will represent, we just want the distinct elements, right? So basically a merging of the three sets, this one and this one, merging. That is, we want to have only those bits set which elements are present, which is set in either one of them. So what we want to do? We want to do a binary OR operation. Yes, not XOR, OR, binary OR. We want to set the bits that are present in either one of them. So not XOR, we want to do a binary OR operation, right? So it will become 1 1 1 0 0 0 1 0 1, and here it is 0, and here also 1 0 0. If we do a binary OR operation, 0 1 1 1 1, see, and in fact this set contains 2 1 2 3 4. This set contains 1 2 3 4. That is represented by this, right? 1 2 3 4. So we'll do a binary OR operation. And what do we want? What is the final answer for a given node? We want to see the number of set bits. The number of set bits should be less than equal to k. The number of set bits in the mask should be less than equal to k. Please speak in Hindi. No, because there will be many people who do not understand Hindi, right? So number of set bits in the mask will be less than equal to k, right? So that is what we want. So that is the final solution. So let's try to write the code for this. Okay. In good subtrees, this and this, let's maintain the answer in a variable here, int answer, right? And here we'll mark it answer equals to 0. And in DFS, so in DFS, int s and int p, node start current. So this represents, what will DFS return? It will be return the mask of the subtree of current. The mask of the subtree of current, right? That is what this int DFS returns. So first is int mask equals to current of data, right? In mask equals to 2 to the power current of data. We are just setting this bit, right? 2 to the power current of data. So we are setting the current of data. If current of data is 2, so we are doing 2 to the power 2. We are setting the second bit, third 0 1 2, right? We are setting the third bit 0 1 2, right? So 2 to the power current of data. Does this do? Okay, 2 to the power current of data, and for, okay, so also if current if current is null, right, current equals to null, we should return a 0 because there is no node, so it will return a bit mask of 0. Now mask or equals to DFS, we are doing a DFS on the left subtree, so current of left, and this will return the mask for the left subtree, this will return the mask for the left subtree. Mask or equals to again DFS of current of right, so this will return the mask of the right subtree, and we are doing odd. Why? Because we want to have all the bits set for all the elements that are there in the subtree, right? So each of these masks will represent the elements that are there, and we want to combine them, we want to merge them, right? So or should be the operation we have already discussed. Now if, okay, so there is a internal method called built-in pop count, I guess. So let's search it, built-in pop count. So that will represent the number of, what is built-in pop count? Built-in pop count is number of set bits, I guess. We have coda. So built-in pop count is number of set bits in an integer, right? So that's what we want, built-in pop count. So we'll just use this. If, or we can calculate manually as well, right? Built-in pop count, but I just want to use this. So built-in pop count, let's hope this works. Mask is less than equal to k. We also need k here, and we can pass this here as well and here as well. Answer plus plus, and finally we'll return mask, right? How to count all set bits using this, or you can just run a loop, right? For int I equals to 0, I less than equal to 25, I plus plus, if the current bit is set, so mask and 2 to the power I, if the ith bit is set, then count plus plus, something like this, right? You can count the number of set bits like this using a loop like this. Okay, so answer plus plus, answer equals to 0. Return, okay, so we'll do DFS root and k, return answer. So that should be it. Okay, right, so that should be it, and we're getting the expected output. So let's try to submit this. So set is definitely one of the solutions, but also you can use bit masking. How do you set 3 as a set bit by left shift? Sure, let's do that. Okay, so what we are doing here, 3, right? Let's clear the board. So what we have done, let's check again what we have done here. Let's say current of data is 3, so we are doing 1 left shift 3, right? 1 left shift 3. What does 1 left shift 3 do? 1 left shift 3. That is, 1 means what? 0 0 0 1. Left shift 1, left shift by 1 place means 0 0 1 0. Left shift by 2 place 0 1 0 0. Left shift by 3 places 1 0 0 0. See, the third bit is set 0 1 2 3. The third bit is set, and that is what we want. We want the third bit to be set because the current element is 3, so the third bit should be set. So that's how, basically, if you want to set the ith bit, simple. If you want to set the ith bit, you can do 1 left shift I. This is basically 2 to the power I. Okay. So 1 left shift I. So 1 left shift 3 is setting the third bit. Okay. So this is how we can solve this. Let's solve the last question quickly. I hope this is clear with everyone. So we are doing nothing, right? We are calculating the mask. Mask is what? The number of the mask for the current subtree. What is the mask? Mask represents the set, the current elements that are there in the current subtree, and we are just returning that mask, and then we are combining the left, right, and the current element, right? How we are combining? Using a binary OR operation, because if an element is present within the subtree, the corresponding bit should be 1. Okay, Let's solve the last question quickly. I hope this is clear with everyone. Let me know if it is not clear with you. Let me know if it is not clear with anyone. Okay, so let's come to the problem minimum sum, right? You are given a tree, a connected undirected graph with no cycles, that is the definition of tree, consisting of n nodes numbered 0 to n minus 1, and also an array weight of length n such that weight of I represents the weight of the ith node, right? Weight of the ith node. So we are given a tree. Again, this is the definition of tree, not very important. N nodes are numbered 0 to n minus 1, and also an array of weight which represents the weight of the ith node. You are given 2D integer array, that which is basically the definition of the edge. Edges I is xy, means there is an undirected edge between x and y, right? For each paired ij of the node, you have to sum the weight of the node with the minimum value. You have to sum the weight of the node with the minimum value that occurs in the similar path between ij. Okay, so it is said that for every pair of nodes ij in the tree, what you have to do is, there is a simple path from I to j. In that simple path from I to j, whatever is the minimum value that is appearing, you have to add that to your answer. And finally, for every pairs, you will do like this, and whatever answer you get, you have to return it. That is what you have to compute. For example, node 1 to node 5, there exists a weight 2 in the path between 1 and node 5, and this weight is minimum, so we have to add this value to our result, and finally we sum the minimum weights of node that occurs in the path and return the value. Okay, so for example, let's take this example, right? I think it's a bit confusing, so let's take this example and try to understand what exactly is asked. So we have 0 2 1 3. How to think of the best approach, like you, it mostly comes with practice, right? But again, like with respect to, like, see, bit masking, it is very, there are some rules that you have to apply as well. You have to know, right? For example, bit masking is mostly used whenever the constraints are within 30 or within 25 30, like this. And also you see, or it can be used in cases where you have to maintain the distinct elements and these things. You have to find whether some element exists and something like that. So in those cases, you can always use a bit mask. And also in the places where the constraint is very less, right? Like 20 25 10, like this. So that's the idea, right? And remaining things, again, like, you have to understand when to use something, right? What is the use case and when to use something, and then you have to see if in the problem you can use that thing, right? If the problem reduces to something like where you can use that corresponding thing that you are thinking about. So it, again, like, it mostly comes with practice, but also understanding as well the basics, right? So 0 2 1 3, 0 2 1 3. Okay, so these are the okay, these are the age weights, or what? Weights are 6375, 6375, 6735. Okay, 6 7 3 5. Okay, let's consider all the pairs, right? 0 to 1. First pair is 0 to 1. What is the minimum weight that comes in the path from 0 to 1? 0 to 1, this path, what is the minimum weight? 3. So 3 is there. Then 0 to 3, let's consider. What is the, or 0 to 2, what is the minimum value that comes in the path from 0 to 2? 6 and 7 are coming, so the minimum is 6. So 6. 0 to 3, what is the minimum value that comes in the path from 0 to 3? So what are the values that are coming? 6, 3 and 5. Minimum is 3. So 3 is there. Then let's consider 1 to 3. 1 to 3, what is the minimum value that comes in the path from 1 to 3? That is 3 and 5, 3. 1 to 2. What is the minimum value that comes in the path from 1 to 2? That is 3, 6 and 7. 3 is the minimum value. Okay. 2 to 1 will not do, because 1 to 2, 2 to 1 will not calculate reverse. Like it is already given in the, I think somewhere it is already given that reverse is not calculated. Reverse is not calculated, right? So we don't have to compute 2 to 1. What is remaining? 2 to 1, 2 to 3 is only remaining, right? 2 to 3. What are the values? 7, 6, 3, 5. So 3 is the minimum out of them. 3 is the minimum. So 3. So what is the total sum? 3 plus 3, 6, 9, 12, 15 plus 6 is 21, I think. Yeah, 21. So 21 should be the answer. Let's see, 21 should be the answer. Yes, the answer is 21. So you have to do this, right? This is the question. Like you have to think about all the pairs, and for each pair you have to find what is the minimum value in the path from that node to that node, right? Okay, so this is the question, and n is 10 to the power 5. That is the constraint, right? N is 10 to the power 5. So obviously if you're thinking of a brute force way that will loop for all pairs of nodes, that will not work. Definitely that will not work. So we have to do something in an intelligent fashion. Okay, let's take a step back, right? Let's take a step back. Can we tell, let's say there is an edge of weight W. Let's say there is an edge of weight W. Can we tell how many times will W appear in our answer? That is, how many times will W be the minimum node? Can we tell this? How many times or how many pairs of nodes are there such that W is the minimum node in path? Can we tell this? Solve similar question in one of lead score contest. That's very good. So you got it common. Okay. Okay. So how many can we tell? Like, can we think about a way? Can we think about a way that will give us this? Let me just arrange my writing pad. Okay. How? Okay. So let's understand this. Okay. How do we tell? So W is here, right? Okay. When will W be an answer? When will W be an answer? Just think about it. Only when the remaining graph, right? Remaining graph has all the edge weights greater than equal to W. Has greater than equal to W or greater than W or greater than equal to W, the remaining graph. And also W should be in the path, right? For W to be an answer, W should be in the path. So let's say we have the current graph. What is the condition of the current graph? The current graph, let's say W equals to 3, right? W equals to 3. So let's say the graph has or the current forest, it will be a forest because it's broken. All the values are greater than equal to, only the nodes are there whose values are greater than equal to 3. Only the nodes are there whose values are greater than equal to 3, right? 4, 5, 6, let's say 4, 5, 4, 4, something like this, right? And there is a connection between them, something like this, let's say. And when we bring this 3, right? When we bring this 3, this basically is connecting like this. This basically is connecting like this. In that case, how many times will 3 become an answer? And all other edges are less than equal to 3, right? Are less than equal to 3. So how many times will 3 be an answer? 3 will be an answer for all of any pair of node between these two sets. Because just think about it. Why? Because any other, it's a tree, right? So there will be no other path. There will be no other path from any of these nodes. So a smaller value will never come. Only bigger values, like let's say we are going from this node. Let's mark it in a different color. Let's say we are going from this node to this node. So in this case, we'll only come across the minimum value 3. There will be, it is not possible to have a node that is less than value of 3, right? Because it is there is only one simple path in a tree. It is a tree, it is not a graph. So that's why. So basically, yes, so basically the answer will be for all these nodes, that is 4 nodes are here, 3 into nodes are here, so 4 into 3 pair of nodes will be there, for which the answer will be 3. So 4 into 3 times 3 will be added to our answer, so into 3. So this is something that we should add to our answer, 4 into 3 into 3. So this is what we will do, right? For every weight we'll find like this how many times it will be in our answer, and we'll then add that value to the answer. But how do we do this? How do we end up with this graph with all greater weights? So what we'll do, let's start with the example only. So let's try to do it with the example only. Let's erase these parts. Anyone has any ideas about how to do this now? Okay. So first thing we'll do is, let's mark all the edges with some value, right? So this edge has edges with some marker. So this edge is called 1, let's say. This edge is called 2. This edge is called 3. So for a edge, what is the value of the edge? Whenever we take a edge, whenever we take this edge 1, whenever we are taking this edge 1, we are seeing two values, 7 and 6. So the value of this edge is the minimum value, right? Because whenever we take this edge, we'll see both of these values, we'll take the minimum one. So the value of the edge is 6 basically, right? So let's move the values to the values of the edges. So what we'll do is, we have the edges, let's write them down here. So 1 has a value of what? 6. 7 and 6, minimum of 7 and 6 is 6. So 1 will have a value of 6, the edge 1. 2 will have a value of 6 and 3. What is the minimum? 3. 3 will be having a value of 3 and 5. What is the minimum? 3. Like this, right? So first thing we'll do is, we will sort all the edges in descending order, and also we'll maintain like what are the nodes it is connecting. So sort all the edges in descending order of the values. So 6, 3, 3, right? Now start with the, what we'll do is, assume that no edge is there. Initially everything is broken. So if here we have 0, here we have 2, here we have 1, here we have 3. Nothing is here. So first of all we'll process this edge. So 6. 6 is between whom? 2 and 0. So 2 and 0 are getting connected with the weight of 6. And how many times 6 is becoming the answer? Only one time between one pair of node. So 1 into 1. So 6 is becoming the answer only one time. So answer equals to 6. Initially answer becomes 6. Becomes 6 into 1 into 1. Let's go to the next node. So this is 2. 2 is connecting between whom? 0 and 1. So 0 and 1. Between 0 and 1, 2 is connecting. 2 is connecting here. So the weight is 3. So how many times will 3 be the answer? There are 2 nodes here. See, there are 2 nodes here. There is 1 node here. So any pair between these 2 nodes and this 1 node will be answer. So that is, number of pairs will be 2 into 1. And what is the value that will happen? Value is, the minimum value is 3. So we get a total value of 6 because of this edge 3. So plus 6. Now let's come to the last value, that is this 3. So this is connecting what? This one. Again, this is connecting this set with this set. So this is the minimum value in this path. So what is the corresponding number of pairs? It will be 3 into 1. Number of pairs means how many pairs between this set and this set we can form. X into y, count 1 into count 2. So 3 into 1 into the value is 3. So 9. So plus 9. And if you see, 9 plus 6 is 15. Plus 6 is 21. So we get a value of 21, which is the answer. Right. Now I think it's clear with everyone. Now I think it makes sense. What we are doing is, we are having sets. We are having disjoint sets, right? We are having disjoint sets. in each, when we are adding a edge, we are combining two disjoint sets, right? These two are sets, set 1 and set 2. We are combining these two sets. So we are doing the merge operation. And what do we need? We want the count. So we have to maintain the count of nodes under each set. So that is what we have to maintain, count of nodes under each set, and that will do, right? How you got the answer? Sure. Maybe let's take a different example, right? Let's see if there is another example. I think this is okay. This is a good, might be a good example. So 1 0. Sorry, let's take the black color only. 1 0 2 4 3. What are the values? 1 6 2 1 6 2 3 5. Okay, 3 5. Okay, listen carefully. What we'll do first is, first of all, think about a edge. What happens when we take a edge? Let's say we are taking this edge 0 and 1. Whenever we are taking this edge, we are encountering two values 6 and 1. What is the value we'll take? We want the minimum value always. So 1 will take. So this edge has actually a value of 1. Whenever we take this edge, 1 will always get a domination over 6. So we can just represent 1 for this edge. So for each of the edges, we'll represent their corresponding values like that, right? So let's represent the values. Let's take a different color. Okay, for this one, this is 6 and 3. So it will be minimum is 3. This node is 1 and 2, 1, 2 and 5, 2. Okay. First of all, what we'll do is we'll sort all the edges in descending order, right? Or ascending order and process backwards. Both are same. So let's sort all the edges in descending order. So what will it look like? First 3 is there, and 3 is the edge between 0 and 4. After that, basically this is the edge value, and this is the node it is connecting, 0 and 4. After that, we have, sorry, we have 1. Yes, after that we have 2, this one 2. It is connecting 2 and 3. After that we have 1, it is connecting 1 and 2. And 1 again, it is connecting 1 and 0. Now just assume all the edges are broken down initially. We have done this. Now assume these edges are not there. Each of the nodes are kind of independent. Nothing is there initially. Okay. Now firstly, we are processing the first edge. We are processing the first edge, that is 304. So 3 is connecting 0 and 4. And 3 is coming here. So what is the number of times 3 will be an answer? It will be only for the pair 0 and 4, 3 will be an answer, because 3 is connecting these two, and number of times is 1 into 1, count of set 1 into count of set 2, because only one pair will be there now, that is 0 and 4. So answer equals to 3. 3 into 1, right? Count number of times. After that 2, 2, 3 is coming. 2, 2, 3, 2. How many times 2 will be an answer? Only for the pair 2 and 5, 2 will be an answer. See that for no other pair, 2 will be an answer ever. So 2 and 5. So again, 2 is only one pair is there, 1 into 1. Now 1, 1, 2 is getting connected. So 1, 1, 2 is getting connected. Now what is the number of pairs for which this will be an answer? See, we have two sets. This is one set, this is one set, that is getting connected with 1. So the number of pairs will be number of cross connections that are getting formed, that is count of set 2 into count of set 1, that is 1 into 2. Because 1, 2, 1, 3, these are the two pairs. So 2, and what is the value? 1. So plus 2. 2 into 1, that is 2. Plus again we have 1, 0. So this is getting connected. Now again, see this. How many sets are, this is one set. This is one set, and these two are getting connected. So what is the number of pairs? 3 into 2. And for each of them, the answer is 1, because 1 is the current edge weight. So 6. So plus 6. So if you see 6 plus 2 8 plus 2 10 plus 3 13. So we get 13 and the answer should be 13. Answer should be 13. Yes, answer is 13. Right. So this is how we are solving the problem. So let's try to write the code for this. So for DSU, we are doing a DSU. So for DSU, what we need? We need a vector int, frequency or the count, and count of nodes in the subtree, and vectoring the parent for DSU. First thing that we'll write is the int find the root of the current node. So int u. Again, like this is the code for DSU. I'm not going into details. If you don't know about DSU, I'll recommend you to first read about DSU, right? So if u equals to parent of u, for only the root nodes will have this condition, so we'll return u. Otherwise, parent of u, we are doing a path compression, equals to find of parent of u. This is basically a path compression, right? Again, it's a DSU algorithm. You can read about it and return parent of u, right? So we are doing a path compression here. Now void merge, we are merging two nodes, int u, int v. Now what we'll do is int ru is the root of u, so find of u. Int rv is the root of v, sorry, rv is the root of v, that is find of v. Now if ru equals to rv, that means they are already in the same set, so we'll just return. Otherwise, we'll set the parent of ru equals to rv. So rv becomes the parent of ru. So the set rv is getting combined to set ru. So the size of rv will increase. So count of rv plus equals to count of ru, because ru is getting combined to rv set, right? Count of rv plus equals to count of ru. Now here we'll do this. So what we'll do first is the vector paired int weighted edges, right? So this will represent what? WUV, like this, WUV. Again, UV is the edge, the node that it is connecting, and W is the weight. Why W comes first? Because you can sort with W, right? So that's why. So for int I equals to 0, I less than edges dot size I plus plus, int u equals to edges I0, int v equals to edges I1, and int weight equals to what? The minimum of the weight of uv. Now weighted edges dot pushback, what will push? Weight and uv, the node it is connecting, right? So first we'll sort this, sort weighted edges dot begin, weighted edges dot end, right? Okay, so this is done. We are sorting in increasing order and we'll process backward, right? So parent, first of all, let's initialize these variables, right? So parent equals to vector int n plus 1, or I think n0. I hope that it is zero based indexed, right? So vector in parent and count equals to vector int, again n0 or n1 also we can do, but we'll run a loop anyways. For int I equals to 0, I less than n, I plus plus, parent of I. Again, this is a code for DSU, right? Parent of I equals to I, count of I equals to 1. This is just a DSU code. So now what we'll do is we'll process in a reverse way. For int I equals to weighted edges dot size -1, I greater than equal to 0, I minus minus. Okay, this is done. Now long answer 0L first is int ru. Okay, int ru equals to, sorry, first let's take u and v. U equals to weighted edges of I dot second dot first. Int v equals to weighted edges of I dot second dot second. Int ru is what? The root. We want the root. We'll always do the calculation whenever it's a DSU. We'll always do calculations with respect to root. So find root u, find root of v, and after that what we'll do is okay, this part is done. Now we need what? In frequency 1 is what? It's the count. Let's see. Yes, count of ru. So first is if ru equals to rv. That is if they're already in the same set, nothing to do, then continue. Otherwise, long f1 equals to count of ru into 1l. Long f2, frequency 2 is count of rv into 1l. Into 1l. Now what we'll do, and also the weight, long weight equals to weighted edges of I dot first into 1l. So f1 is the frequency, f2 is the frequency, number of pairs will be f1 into f2. So answer plus equals to f1 into f2, and what will be the weight? Wt. So that will be the answer. So this is the total answer. So return answer. So that should be the code. Let's try to run this. How did you come up with this idea within just 2 minutes? How did you know that? I have already solved this problem, right? I already knew about this. But this problem, again, as I said, it comes with practice, right? So this is a very similar problem to Spoj Koi cost. There is a problem called Koi cost, right? You can see here Koi cost, Spoj. This problem is very similar to this one, and it also uses a similar concept as well, right? You can definitely, this is a harder version of that one. So again, like that comes with practice, as I said. Like when you have practiced enough, you will understand that this is a problem that is similar to something existing if you have solved the existing problem. So that's there, right? But yeah, I had already solved this problem, so that's why I knew it's a DSU question. Okay, so 12. Why did I get 12? 1 second. Weighted edge. Yes. We are not calling merge here, right? So after this, we have to merge u and v. So merge u and v. Let's call this. Now let's compile and run this. So 21 comes here. Now let's submit this. I think this should work. But yeah, let me know if you have any doubts. Yes, this is working. So let me know if you have any doubts around this, like any doubts, any concerns, anything around this. Again, like this was a good problem, and I think you learned from something, learn something here. Like whenever you have questions where you see like you can actually, you are merging and you have to find all the pairs and paths and these things, then maybe it's a DSU question. Apni Bengali? Yes, I'm a Bengali. Cool. Okay, so any concerns around this? Otherwise, we can call it a day. Anyone has any doubts? I'll wait for 1 minute maybe. Let me know if you have any doubts. Cool. I don't think you have any questions. So yes, definitely solve this problem on your end. Like I've already discussed the solution. If needed, rewatch the video. Don't see the solution. Rewatch the video. Understand the concept. Try to write the code yourself. Then you will understand this better. Like how exactly things are working. Right. So do that. Otherwise, Shubho Kali Pujo. Okay. Okay. So all right. Thank you for joining in. And yeah, I'll be seeing you in the next class, right? Next Sunday. So thanks and bye, and happy Diwali.